Let us now continue our discussion on cache memory. So basically, uh, cache memory is one of the main uh, parts or design or what do you call this, part of computer architecture. No? Basically, uh, dito nilalagay yung mga data that you have to run in order for your computer to work. No? Dito sinisave lahat ng mga data or instructions before before your computer operates. No? So here are some of the key characteristics of computer systems. No? So the location, the capacity, the unit of transfer, the method of accessing, the performance, the physical type, physical characteristics, and organization. No? So I think uh, with the schedule that I'm current in, baka hanggang final sa itong discussion natin sa memory. No? Anyway, let us fast track na lang our discussion. So in cache memory, we have capacity, no? The number of words and the number of bytes. No? Ano ba yung word? Word basically is the natural unit of organization of memory. No? The size of a word is typically equal to the number of bits used to represent an integer and to the instruction length. Okay? So for example, no, ito ang magandang explanation dyan. No? Think of a word as a chunk of information, no, that a computer can handle. No? Imagine a word as a piece of paper with a certain number of spaces for writing numbers. No? The size of the word is how many spaces there are. For example, some computers might have words that can handle 64 numbers. Some might have words that hold 32 numbers. So dito, ang word na tinatawag is yung information mo kung saan siya ang nag-handle ng chunk ng information. Okay? Ang pinakamagandang example dito na binigay, no? Meron kang isang blank piece of paper na kaya siyang pagsulatan ng 64 numbers or 64 words. No? So that's typically the word is, no? In the context of cache memory. Okay? Ano naman ang addressable unit? When we say addressable unit, this refers to the smallest unit of memory that can be individually addressed. In some systems, the addressable unit is the word, but in many modern systems, it is a byte. Ngayon, ayan kung kanina is word, the typical unit before, but ngayon, it is called byte. So most of the time, computers think of memory in terms of tiny blocks called bytes. No? Each byte is like a single block of storage. If you imagine your memory as a giant box with lots of drawers, each drawer would be a byte. When you tell the computer to look in a specific place in memory, it's like giving it the address of a drawer. The more bits, smallest pieces of data you can use in an address, the more drawers the computer can keep track of. So, for example, meron kayong to sa tabi ko. Sa tabi ko meron ako ditong steel cabinet. Itong steel cabinet na to, meron siyang kanya-kanyang drawer. Kung saan, bawat drawer is merong laman na memory or space. So ito, every time na meron kang ilalagay dito na bit or bits, no? Yun yung space na kaya niyang ilagay. For example, itong drawer na to is 64 bits. Kaya niya ilagay. Sa next drawer niya is 64 din. The next is ganun, ganyan. So that's addressable unit. So itong address na ganitong nasa taas, address pangalawa, address pangatlo, yung gawa ng data sa computer mo. Okay? In bytes or in bits. Okay? So unit of transfer, ano naman ang tinatawag na unit of transfer? So for main memory, this is the number of bits read out of or written into memory at a time. The unit of transfer need to not equal a word or an addressable unit. For external memory, data are often transferred in much larger units than a word, and these are referred to as blocks. Unit of transfer, think of it like a scooping water out of a bucket. The scoop, yung pagkuha mo niyan, can be bigger or smaller depending on how the computer is set up. For example, some computers can move big scoops of 64, 128, 256 bits of information at once. This doesn't always match how big a word or a byte is. Sometimes the scoop can be bigger. So ito naman, unit of transfer typically means the way how big the information can be addressed and scooped or transferred into other unit. No? Sa example na binigay sa atin, mayroong 64-bit, may 128-bit, mayroong 256-bit na information na kayang i-transfer at a given rate. No? Depending sa setup ng yung PC or the capacity of your CPU, the capacity of its memory. Minsan meron siyang 256 gig bits of data that can transfer. No? So, depende yan. Depende sa kung anong meron system ka ngayon. So, those are the some of the characteristics of cache memory. Meron siyang bit or byte, or before is word. Meron siyang addressable unit kung saan nakalagay yung mga data. Okay? And yung unit of transfer. Kung paano siya mag-transfer. Okay? So, in summary, a word is a chunk of data the computer uses at once. So, typically ngayon, bit or byte. An addressable unit naman are tiny piece of memory that the computer can find. And the last one is the unit of transfer, how much data a computer moves at one time. So that's some of the important idea on cache memory. The word or the byte, the addressable units, and the unit of transfer. So now let us watch the data transfer instructions. 5 minutes lang naman siya.
Now we're going to talk about data transfer instructions. These are instructions that allow us to move data between the memory and the register file. So in order to do that, we're going to have to add some more stuff to our processor. So the ALU is going to generate our address, but we need a place to put that address so we can get it to the memory. So what we're going to do is we're going to add a memory address register. And so this is a place where that address can go so that we can get ready to send it off to the memory. We also need a place to store results that are coming to or from the memory, and that's going to be a data register. So this is where the data is going to go back and forth. So if I'm using that address to access memory, I can put the data I got into that register. Now, once you've got the data in there, then you can go ahead and write it back into the register file. So we've added two things. We've added a memory address register and a data register. Now let's take a look at an example of doing a load word. So here's our program. We're going to do an add I R5 R0 12. This is going to add 12 and 0 and store it into R5. And then we're going to load word. We're going to load the address, the data at memory address in R5, which will be 12, into register R6. So let's take a look at this program. So we start out with instruction 0. We move it into our instruction register. And our control tells our ALU to do an add. It's an add instruction. And the register file what data to use. Now this is an add immediate instruction, so we're going to get some of the data from R0 here, but we also need some data from this 12. So we're going to take some of the data from 0 and some of the data directly from the instruction. So that 12 is in the instruction, and we're going to send that 12 right down to the ALU. We add those together, and we write back into R5 and write into 12. Now we go on to the next instruction, which is instruction 4. This is now our load word instruction. So we go ahead and load the instruction. The control is going to tell the ALU, just pass the address through for now. And which address is it going to be? Well, it's going to be the address at register 5. So we're going to pass the 12 through into the memory address register. And then we're going to go to the memory, and we're going to tell the memory to read the data at address 12. So when we read that data, it's going to take it back and put it into the data register. And then we can go ahead and write that back into the register file. So now we've loaded the data that was at address 12 from the memory into the register file. So the important thing to note here is that we used the address from the register file. So we had to have this address 12 in the register file so that we could know where we wanted to access in the data. Now we can also put offsets on memory instructions. So for example, load word R6 for R5. This says load it at 4 bytes off from R5. So we can go ahead and put this in here. Now our instruction looks like this. And this is going to be 4 bytes off of R5. So how is that instruction executed? Well, let's take a look. So here's our instruction in the instruction register. This is a load with an offset. Now our control is going to tell the ALU to do an add. And what's it going to add? Well, it's going to add the value in R5 and this 4 from the instruction. So we take the value in R5 and we take the 4 from the instruction, and we're going to get 16. Now we're going to do the load. We're going to go and access the memory at location 16, and we're going to load it into our data register, and then finally write it back into our register file. So at this point, you should notice a similarity between the load word instruction with the constant offset and the add I instruction with the constant offset. And indeed, we'll talk about that similarity in the next lecture when we talk about instruction encodings. So let's take a look at an example of storing something. So to store stuff, we need to know the address from the ALU, where in the memory we're going to put it, and the data that we're going to store in there, which we're going to get out of a register. So let's run through this program. So we're on instruction 4, which is store word. So we're going to take that. The ALU is going to do the same thing it did for load word. It's going to pass through, and what's it going to pass through? Well, the register that tells us where to store it. In this case, R5. We'll use that as the address. And then we take the data out of the register file, which is the data that we're going to store, in this case register 6. Put that in the data register, and then we write to the memory, and we're going to put that data into location 12 in the memory. And that's how a store works. So a question about accessing memory. Why do we need both a memory address register and a data register to access the memory? Well, the reason for this is we need to know both the address, that is where in the memory do we look, and what data are we reading or writing from it. So we need 2 pieces of information when we go to access the memory. You can see this in the store word instruction, where we need to have the memory address and the data in order to go and do the store. Here's another question. Where does the offset come from when we have an offset load? Well, in this case, the offset comes from inside the instruction. This is an immediate instruction because it has this immediate value inside the instruction. And when we processed it, we saw that we were doing an add in the ALU, and the control told the register file where to get the data from. Part of it came from register 5, and part of it came from right here in the instruction, that value 4. And we used that to calculate the memory address for the operation.
So basically, that video is about how you transfer the data from one addressable unit to another, no? So makita nyo doon yung kung saan may mga instruction sets na tinatawag. Then yung mga instructions na yun, lalagay siya sa isang addressable unit, sa isang cache memory. Then tuloy-tuloy na yung pagpasok ng pag-transfer ng data. Okay? So how does the cache memory is accessing those data? No? So the method of access in cache memory depends on how the system is being designed. So in this slide, we have 4 methods of how this data is being accessed. No? So it's part of the characteristics of computer memory systems. As you can see, the 4 methods of access in cache memory. We have the sequential, the direct, the random, the associative method of access. So let us define each kind of access. No? So ano ba ang tinatawag na sequential? When we say sequential, memory is organized into units of data called records. Access must be made in a specific linear sequence. Ibig sabihin, tuloy-tuloy siya dapat. No? Stored addressing information is used to separate records and assist in the retrieval process. A shared read-write mechanism is used, and this must be moved from its current location to the desired location, passing and rejecting each intermediate record. Again, sabi dito, the sequential, from the word sequential, sequence, no, the access or the method of access must be specific linear, so tuloy-tuloy. So to give you an example, no, this is like reading a book from start to finish. If you want to find something near the end, you have to go through everything that comes before it. The computer has to go through the memory one step at a time, like flipping through the pages. So hindi ka pwedeng tumalon na lang bigla. Halimbawa, naghahanap ka ng isang data or ng isang idea. Hindi ka pwedeng tumuloy ka na kagad dun sa page na yon or sa drawer na yon. But you have to scan all through the pages, all throughout the pages. Na hindi ka pwedeng tumalon. Kailangan mong mag-start sa umpisa hanggang sa dulo, kahit nasa pinakadulo na hinahanap mo, dapat mag-start ka pa rin sa umpisa. So that's sequential method of accessing the data in cache memory. Okay. The next one is the direct method of access. Ano ba itong tinatawag na direct method of access? Access is accomplished by direct access to reach a general vicinity plus sequential searching. So from searching, counting, or waiting for to reach the final location. Again, access time is variable. So this is like going to a specific shelf in the library where you know the book is, but you might still have to scan the shelf to find the exact book. For example, di ba kanina sa may sa sequential ang binigay example is libro. Then kailangan pong basahin from page 1 hanggang page 300 for example to find the data that you're looking for. Indirect naman, indirect approach, indirect method of access, no? For example, alam mo na yung page niya, for example, nasa page 100 yung hinahanap mong data. Pwede kang tumalon doon, but again, meron kasi mga chapters siya, for example, chapter 10. So chapter 10 from page 90 to 100. Pwede ka nang dumiretso doon sa chapter 10 kaagad. However, you have to make sure that basahin mo muna yung page 90 to 100 before mo makuha yung data. Before mo makuha yung information na gusto mong kunin. So that's direct approach. Again, dito binigyan example sa library pero medyo malawak na. Doon sa sequential, you have to make sure that you read the first page at the last page before mo makuha yung data na hinahanap mo. For example, yung data mo is nasa page 99, mag-start ka pa rin sa page 1. So that's sequential. Sa direct, pwede ka nang tumalon sa page 90 up to page 100. But again, mas naging narrow yung paghahanap mo ng data pero kailangan mo pa rin basahin yung page 90 to page 100. So that's the method of access. Mas mabilis siya ng bahagya. Okay? So that's direct method of access. The third one is the random access method. No? When we say random access, a random method, no? Each addressable location in memory has unique physically wired in addressing mechanism. The time to access a given location is independent of the sequence of a prior accesses and is constant. Thus, any location can be selected at random and directly addressed and accessed. Main memory in some cache systems are random access. It's like going straight to the book you want in the library without having to look at anything else. So again, that's random method of access in the way you access the data, no? We have the random access. Kung dito, mas narrowed na yung paghahanap mo ng data. Okay? Each addressable location in memory has a unique physically wired in addressing mechanism. So kanina, ang example natin is libro. Yung sequential mo is from page 1 to 100. Babasahin mo lahat. Sa direct is magiging narrow siya from page 90 to page 100. But in the random access, method of access, pwede ka nang pumunta ka agad sa page 99. Okay? Kasi meron na siyang specific address, physically wired in addressing mechanism. The time to access a given location is independent of the sequence. Wala siyang pakialam kung anong sequence pa siya. Kasi meron na siyang address, meron na siyang physical address na pwede niya napuntahan kaagad. No? Any location can be selected at random and directly addressed and accessed. Kung nasa page 99 yung data mo, pumunta ka ng page 99. Kung nasa page 20 yung hinahanap mong data, punta ka sa page 20. So, karamihan ng memory ngayon is random access. No? So, yeah, the best example here is like going straight to the book you want in the library without having to look at anything else. So that's random way of accessing the data, no, in cache memory. The fourth one is the associative method of access. This is a random access type of memory that enables one to make a comparison of desired bit locations within a word for a specific match, and to do this for all words simultaneously. Thus, a word is retrieved based on a proportion of its contents rather than its address. No? This is a special kind of random access. Instead of looking for something by its address or location, the computer looks for it by matching its contents. Imagine going to the library and finding a book because you remember part of a sentence inside it, rather than knowing the title or where it's kept. The computer checks all the data at once to find the one that matches what you're looking for. So itong associative method of access is like random, but again, comparing this data from other pages. Now, for example, you are looking for a name sa isang book at ang pangalan ng name is Honey Lane, no? Halimbawa, yan ang name nung hinahanap mong data, no, sa isang libro. Ngayon, na-mention yung word na Honey Lane ng 10 beses every 10 pages. So, sa associative way of accessing the data is again, damputin niya yung first 10 pages, damputin niya yung second pages, yung chapter 1, chapter 2, chapter 3, up to chapter 10. Then, kukuha niya lahat ng name na hinahanap mo. Then, pipiliin niya doon kung saan ba yung pinaka-best match sa hinahanap mo. No? So, that's associative method of access. So, again, yung Hanrin po is yung kasama namin dito sa opisina. No? Ako namin dito sa ICT division. So, that's the 4 access methods of data in cache memory. No? The sequential, the direct, the random, and the associative methods of accesses. So, ano ba ang sequential again? Summary lang natin. No? When we say sequential, it is slow. Again, basically, it is slow kasi from page 1 to page 100, hanapin mo yung data mo. Step by step, punta ka ng page 1, chapter 1, page 20, chapter 2. No? When we say direct access, you can skip all the entire chapters. Pero pag nandun sa chapter 10, yung hinahanap mong name or data, iscan po rin yung entire chapter 10 from page 90 to page 100. Okay? But sa random access, direct to the point. Punta ka ng page 99 kasi nandun yung hinahanap mo. Okay? Sa associative access naman, so, okay, yung nahanap mo pangalan nasa chapter 1, nasa chapter 10 din. Okay, kunin ko tong chapter 1 and chapter 10, compare ko, then hanapin ko kung saan ba talaga yung pinaka-exact spot or exact match ng hinahanap mong data. So that's cache memory methods of access. No? So to further understand the methods of access in cache memory and how the memory works in a computer and through its sequencing instructions, I have here found reliable videos or videos that you can watch to further understand how the memory works and how the data is being instructed in a sequential way. No? Panoorin na rin natin to. It's a short video lang naman, 12 minutes. Then after this, we can now, I think we can now end this topic.
Now we're going to
In many ways, our memories make us who we are, helping us remember our past, learn and retain skills, and plan for the future. And for the computers that often act as extensions of ourselves, memory plays much the same role. Whether it's a 2-hour movie, a 2-word text file, or the instructions for opening either, everything in a computer's memory takes the form of basic units called bits, or binary digits. Each of these is stored in a memory cell that can switch between 2 states for 2 possible values, 0 and 1. Files and programs consist of millions of these bits, all processed in the Central Processing Unit, or CPU, that acts as the computer's brain. And as the number of bits needing to be processed grows exponentially, computer designers face a constant struggle between size, cost, and speed. Like us, computers have short-term memory for immediate tasks and long-term memory for more permanent storage. When you run a program, your operating system allocates area within the short-term memory for performing those instructions. For example, when you press a key in a word processor, the CPU will access one of these locations to retrieve bits of data. It could also modify them or create new ones. The time this takes is known as the memory's latency. And because program instructions must be processed quickly and continuously, all locations within the short-term memory can be accessed in any order, hence the name random access memory. The most common type of RAM is dynamic RAM, or DRAM. There, each memory cell consists of a tiny transistor and a capacitor that store electrical charges, a 0 when there's no charge, or a 1 when charged. Such memory is called dynamic because it only holds charges briefly before they leak away, requiring periodic recharging to retain data. But even its low latency of 100 nanoseconds is too long for modern CPUs. So there's also a small, high-speed internal memory cache made from static RAM. That's usually made up of 6 interlocked transistors, which don't need refreshing. SRAM is the fastest memory in a computer system, but also the most expensive, and takes up 3 times more space than DRAM. But RAM and cache can only hold data as long as they're powered. For data to remain once the device is turned off, it must be transferred into a long-term storage device, which comes in 3 major types. In magnetic storage, which is the cheapest, data is stored as a magnetic pattern on a spinning disk coated with magnetic film. But because the disk must rotate to where the data is located in order to be read, the latency for such drives is 100,000 times slower than that of DRAM. On the other hand, optical-based storage like DVD and Blu-ray also uses spinning disks, but with a reflective coating. Bits are encoded as light and dark spots using a dye that can be read by a laser. While optical storage media are cheap and removable, they have even slower latencies than magnetic storage and lower capacity as well. Finally, the newest and fastest types of long-term storage are solid-state drives, like flash sticks. These have no moving parts, instead using floating gate transistors that store bits by trapping or removing electrical charges within their specially designed internal structures. So how reliable are these billions of bits? We tend to think of computer memory as stable and permanent, but it actually degrades fairly quickly. The heat generated from a device and its environment will eventually demagnetize hard drives, degrade the dye in optical media, and cause charge leakage in floating gates. Solid-state drives also have an additional weakness. Repeatedly writing to floating gate transistors corrodes them, eventually rendering them useless. With data on most current storage media having less than a 10-year life expectancy, scientists are working to exploit the physical properties of materials down to the quantum level in the hopes of making memory devices faster, smaller, and more durable. For now, immortality remains out of reach for humans and computers alike.
Now we're going to talk about sequencing instructions. These are the instructions we use to use branches, if-then-else statements, and loops. Anything where we're going to do different things depending on the data. So sequencing instructions make decision. The decisions they make are what instructions to execute next. Should we do the next instruction or jump somewhere else? They change what's called the control flow of the program, where the program is going. So MIPS has two conditional branch instructions, and they are BNE, or branch not equal. So this instruction is going to say that if register 0 and register 1 are not equal, then the next instruction goes to this label address. If they are equal, then the next instruction just goes on to the next instruction. And there's also branch equal. And branch equal branches if they are equal. So here if R3 and R4 are the same, then we go to the label instruction next, otherwise we go on to the instruction after this. So let's take a look at an example. I want to do the following code. If I is equal to j, then h equals I plus j, otherwise we do something else. So I'm going to put my data in registers, so R1 is I, R2 is j, and R3 is h. And now we're going to write out the MIPS code for this. So I'm going to do branch not equal R1, R2, skip. So this is going to say if R1, which is I, and R2, which is j, are not equal, I jump to skip. So if they're not equal, I'm going to jump to skip. Then I'm going to have add R3, R1, R2. This is the same as this line here. So if they're not equal, I'm going to jump to the skip, and the skip is right after here. So what happens here is if they're not equal, I'm going to skip over the addition. If they are equal, I'm not going to skip the addition, and I'll do the addition. So that gives us the execution we want here. So here's my conditional branch. If they're not equal, I skip over the next thing, and then I'm done. But if they are equal, then I'm going to go ahead and do the addition, which is exactly what I want in the code. In addition to conditional jumps, we also have unconditional jumps. So jump label just jumps regardless of anything else. It always says go to the label. So let's take a look at an example here with an if then else. So here's the example I had before. If I equals j, I'm going to add I and j. If they're not equal, then I'm going to subtract them. So how do we write this code? So I'm putting my values in the same register files. I'm going to do the same thing here. I'm going to do my first branch not equal R1, R2. So if I and j are not equal, I'm going to jump down to do else. If they are equal, I'm going to continue and do the addition. Then I'm going to jump to skip else. So if they are equal, I'm going to do the addition and then skip the else. If they're not equal, I'm going to jump to do else, which is down here. And right after do else, we have the subtraction. And then right after that, we have skip else. So let's take a look at what this is doing. So if I equals j, we're going to want to do this addition here. So we do branch not equal. If they're not equal, we're going to skip the addition. So if they're not equal, we skip over the addition and go down to do the else part of the code. If they are equal, we go ahead and do the addition, and then we need to make sure we don't do the else part. So we have this jump which skips over the else part. So if they are equal, we do the addition and then we skip over the else part. And if they're not equal, we skip over the addition and we do the subtraction or the else part. So this is how we use an if and else. We need both an unconditional jump, so we always skip over the else part if we've done the if part, and we need a conditional branch so that we decide whether we should do the else part or the if part. So these instructions change the program counter. They change the flow of the instruction, and we've seen two of them. We've seen jump, which goes to a label no matter what, and the branch not equal and the branch equal, which only go to the label if the registers are equal or not equal. Let's take a look at another example. So here we have if A equals B, then C equals 1, else C equals 2. So here's the code, and let's figure out how to do this in MIPS. So we've got our registers. So A is in R5, B is in R6, and C is in R7. They're color-coded to be easy to see. So the first thing we're going to do is branch not equal R5, R6, else. So if they're not equal, we're going to skip down to the else. Make sense? If they are equal, we need to set C to 1. How do we set C to 1? Well, we do add immediate, and what do we add? We add R0 and 1. So this is always 0, so this is going to do 0 plus 1 and store it into R7. So that's going to set C to 1, if we do the if part. Now, if we've done the if part, we need to make sure we don't do the else part, so we'll put in the same jump, skip, else that we had before. Otherwise, if we get down to else, here we need to set C to be 2. So how do we set it to 2? Well, we use another add immediate again. We're going to add 0 plus 2, so R7 will be 2. And then and then here's where the skip else is. So if we're not setting it to 2, we jump down to here. So what happens here? Well, first we check and see if we should do the if part. And if we shouldn't do the if part, then we jump down here and skip to the else part. If we should do the if part, we're going to go through here. Here's the else part. Now when we do the if part, we do our addition, and then we need to skip the else part, so we have this jump to skip over the else. So the key thing to remember here is we're using this conditional branch to decide whether we should do the if or the else, and then if we do the if, we use this unconditional jump to make sure we don't also do the else. Let's take a look at how a loop works. So here's a loop for j equals 0 while j is less than 10. We increment j, and what do we do in our loop? We do b equals b plus j. Here are our registers. So what do we start off with? Well, we start off putting 0 into R5. So we need to set j to be 0 at the beginning. Now we're going to want to check and see if j is less than 10, but we can't compare to 10. We can only compare between registers. So if we want to compare j and a register, we need to put 10 into a register first. So here we go, we do add I, R1, R0, 10. This puts 10 into register 1. Now we can go and do the comparison, because now we have 10 in register 1, and now we can do a branch equal between R5, which is j, and R1, which is 10, to do this comparison. So now we're saying if j equals 10, then we're going to go to exit. If j is not 10, then we go ahead and do the addition. We increment j by 1 by doing an add immediate, and then we branch up here, we jump back to do the loop again. So here's our loop instruction, which is checking if we should exit. And if we do exit, we go down here. And when do we exit? We exit when j is 10. So if we exit when j is 10, this loop is going to be true as long as j is less than 10 because we're incrementing j by 1. Now what do we do for our loop? Well, we go through and we do the additions in the loop, and then we go up and we repeat it again. So here's our loop. We go around and around until we get to j equal to 10, and then we exit. And as you can see here, this exiting part of the loop, this jump here, is basically the equivalent of this curly bracket in our for loop up there.
Anyway, again, to continue. So those were the videos that I think very helpful or useful sa atin when it comes to computer architecture and organization. No? We're able to tackle or to view or watch how these instruction sets are being looked or being sequentially processed, no, in a manner of transfer, a unit of transfer, no, through bits, bytes, and the way the transfer of data works in a computer system. No? So to have a to summarize, no, we're able to tackle the last slide in our prelims, the clock speed, no, and we're able to have grasp on how computer CPU core counts work, the CPU speed, which of the following matters most, yung bang core count niya or yung clock speed niya, and the battle between the Apple Silicon and the Intel i9, the computer architecture, the CPU architecture they built that runs inside a computer, of course, no? And the definition of the computer, the central processing unit. And to move on sa ating midterm, we're able to study some of the basic or the key characteristics of computer memory system. We have the word, the addressable unit, and the unit of transfer. When you say word or the bit or the byte, these are the spaces. These are the spaces that you can handle specific data. No. The second one is the addressable unit. Each data has their own specific address, which your computer or your central processing unit can access anytime. No. These data, these addressable units have data in it now, which is being transferred in various ways. Okay, so this data, which has their own addressable unit, can be transferred in various ways. Again, by the data they have, by the capacity or the memory that they have, no, that it has. So, for example, yung data mo, meron siyang 64-bit na data. Then, transfer siya by bit or by block. Depende yan sa setup ng yung CPU. Okay, so those are some of the key characteristics of cache memory: the bit, the byte, the addressable unit, and the unit of transfer. To summarize, the words chunk of data. Addressable unit, these are the addresses of those chunks of data. And the unit of transfer is how this data is being transferred one at a time. Okay, so we also have here the methods of access. We have 4 methods of access of data in cache memory: the sequential, the direct, the random, and the associative methods of access. When you say sequential, from page 1 to page 10, hanapin niya yung data mo, regardless of whether or not it's on the page 9, on the page 5, no? You have to start from the beginning and finish the entire pages. That's the sequential method of access. Second one is the direct method of access, wherein it will limit you or narrow down your search area. For example, from page 1 to page 10, nakita niya nasa page nasa chapter 1 yung data, then i-scan mo pa rin siya, no? Again, yung example na binigay sa inyo kanina, from page 1 to page 100, meron siyang chapters 1 to chapter 10. Then yung direct, pupunta ka sa chapter 10 to access the entire data. But again, from page 90 to page 100, babasahin mo pa rin yun bago mo makuha yung data na hinahanap mo. When we say random method of access, you can basically directly access the data. For example, your data can be found on page 99. Then your cache memory can directly get the data and process the entire data. So that's the random access method in cache memory. When we say associative way of accessing the data, for example, you're searching for a data number 10, for example, which can be found across the pages from page 1 to page 100. Then each chapter meron siyang data na hinahanap, no? Kukunin niya yung mga data na yon, and then i-scan niya yon, chapters 1 to chapter 10. Then pipiliin niya which data is basically matches your search. So for example, ang pinaka malapit sa search mo is nasa chapter 5. Then yung data na sa chapter 5, regardless of whether or not meron siyang ibang kaparehas, is pa rin chapter 5 kukunin niya. Kasi tingin ni CPU, yun yung pinakamalapit na data na hinahanap mo. So that's method of access: the sequential, the direct, the random, and the associative method of access. So I think that concludes our topic for today. Let us continue our discussion on the next meeting, maybe next week. Again, the same time, same place. Let us see kung may mga adjustments tayong gagawin. So thank you very much. See you again soon.